So today we're going to go over our CS307 final project, which we called InfiniBuilder. My name is Andrei Cozma.
And I'm Hunter Price. The project goals and development process for this project, we basically wanted to learn development on a new platform, learn new language, learn new tools, where really the possibilities were endless. We decided to use Java as our language with the JavaFX graphics library. And we used the Maven build system to make it cross-platform. A couple of goals in mind when we started it. We wanted to create a 3D open world game, and we wanted to implement as many data structures as we could. The possibilities were really endless. And we had no specific time goals for the project. At first, I think our total hour goal was 100 hours total for the two of us. And it ended up being a little over 200 total.
Here's a quick overview of some of the main features that we got to implement within the game. As part of the environment, we implemented infinite terrain generation using Berlin noise algorithms. With that, we had to figure out a collision detection system from the player with the environment. We also got to implement a skybox with the full day-night cycle. The player includes running, jumping, falling, and swimming physics. The player HUD, inventory, and status bars are all controlled by that player class, including health, stamina, and hunger. Spawnable structures that we implemented include maze, path, a grapher util, and a pyramid. We have the ability to place and toss any inventory object as well as spawnable structures. The settings in the game, since it's so flexible, are fully customizable, and they pertain to all of the features from all the sides throughout the game. We have lots of data structures used all throughout, and then we created a cross-platform Java jar executable.
The main data structures we use were hash tables, trees, disjoint sets, and adjacent lists. Basically, a hash table is going to be used when you have a lot of data and you need to look up a value based off a key in constant time. We use them all throughout our project. Trees, typically they have a log n time for most operations, and we used a few of them because they were much easier to traverse through compared to hash tables in Java. We use disjoint sets. Those are very useful when needing to know the connectivity between a bunch of nodes, where if there's a connection between two nodes, and we use those for a couple of classes as well. Adjacency lists used for when representing a graph. The other adjacency matrix is also used to represent a graph, but we use a list. That's very useful for when you want to represent a graph in any context, really. You can use BFS, DFS, or Dijkstra's to traverse through them.
Here is one of the main features which uses one of these data structures. It's the infinite terrain generation. The infinite terrain generation uses two interpolated simplex noise algorithm with different height values. This allows for rocky hills, mountain peaks, as well as flatter valleys, deserts, as well as oceans. Multi-maps are used to keep track of what needs to be generated, what is already generated, and what needs to be rendered on the screen. And this is done in order to keep performance at its highest. Our environment util class totals 580 lines of code. This is a visualization of how terrain generation works. Assume that the player is at 0, 0 on a 3D coordinate plane. From that, we take the X and Z coordinates, feed it into the simplex noise algorithm, interpolate two versions of that same simplex algorithm, and then we get a Y value out. If we take multiple of those Y values from the X and Z coordinates throughout the entire grid around the player, we can construct a height map in order to generate our terrain around the player. The skybox contains a day and night cycle. The sun, moon, and the big neighboring star rotate around the playable area. They have a slight actual rotation to mimic their actual behavior in real life. They have configurable ambient light, period, fixed time, visibility, scale, and distance. The total Skybox util class contains 500 lines of code. The player class implements all movement mechanics as well as running, jumping, falling, and swimming physics. It controls all other aspects of the game, including the HUD, the inventory, status bars for health, stamina, and hunger, which all interact with the movement system as well. The 3D rotational object placement takes advantage of all the structures and the objects that were implemented on all the other sides of the game. The player util class is a total of 850 lines of code.
Throughout our game, we made a bunch of objects and spawnable structures, which includes 5 base interactable objects and classes: a cube, a sphere, cylinder, and a 3D model. In this picture here, you can see a few of them. You can see the sphere, some cubes, and some cylinders. And we had 4 spawnable structure implementations, which basically is a maze, a path, a pyramid, and a grapher. We had a projectile class, which was used to throw the objects if you wanted to. And these structures are all interactable and can be placed in the player inventory, and then the player can retrieve them and place them into the environment. So for the maze generator, we basically set up a grid of walls, and then we chose random walls to break. And when you broke a wall, you would add the 2 nodes that the wall was separating into the disjoint set, and you would union them, and you would continue until all of the nodes have been unioned. And that's shown here. The list of walls on the right is basically the numerical representation of how we held the walls. And so when we would break a random wall, say 1 and 4, we would union the 2 and then continue to break random walls and delete them from the list of walls until we got a size of, or where all the nodes were connected. And then the list of walls on the right is what walls we would draw on the maze. The path generation and shortest path, the path uses this maze generation class and draws the walls that we deleted, which is basically the path in between what the maze walls would have been. And in using these deleted edges that we found, we can make a path visualization, or not a path, a graph representation where each of the deleted walls represents an edge between the nodes. And in using that, we can define a starting and ending position and use any of the 3 searches through a graph that we made, a BFS, a DFS, and a Dijkstra search. Here we're showing a BFS where we start at 0 and we iterate through and visit 2, 4, then 3, then 5, and then finally 8. And then we're going to backtrace from 8 to 5, and 5 to 4, then 4 to 1, and then 1 to 0. And the shortest path is our shortest path, in which we use to draw that red-looking path that was over the top of the maze.
So this diagram is a representation of our Java class structure. It includes all the connections and function calls, as well as variables used between classes, as well as Java packages. All these connections show all 43 of the classes that we have. This is another representation of a small piece out of the game components that are used in order to make the game run. As you can see, the game builder contains the game components subclass, which calls all the utils, such as camera util, controls util, environment, HUD, menu, and player, as well as main execution that is run by game launcher, which in turn uses all the other packages and functions on the right. Some statistics: we have a total of 54 Java classes, 43 textures, 6 3D models, over 10,000 lines of code, and a total of 200 hours spent on this project. In conclusion, in order to download this game, all you have to do is go to this website, install the Java 11 JDK, and run it.